Hello physics students. In this video, we're going to continue our studies of nuclear physics. We're going to pick up where we left off in the last video, Nuclear Physics 1. But before I go into today's information, I want to review some important ideas we learned about nuclear reactions in the previous video. So remember, nuclear reactions differ from chemical reactions in that what's changing is the nucleus, the proton and neutron arrangement in a given atom. So what can happen, or what does happen, is we start off with one kind of element or elements, and we end up with a different kind of element or elements. So in one kind of reaction, we have a fission reaction where we have a big nucleus splitting up into smaller nuclei, and therefore we have one element and two new ones after. Then we studied fusion reactions where we had multiple nuclei bonding together, forming a new nucleus that's larger. And then we also learned that there were three things that were true in all nuclear reactions. The number of baryons remains constant or is conserved. You might have a loss of neutrons as long as you have the same gain in protons, or you could have a loss in protons as long as you have the same gain in neutrons. So baryons conserved. We also learned that charge was conserved. Whatever positive the original nuclei were, when you sum up all the positive of the protons, you've got to have the same amount of positive after the nuclear reaction. But the third, mass was not conserved and energy was not conserved. Those two laws, the law of conservation of energy, law of conservation of mass, are false. And I talked about this already earlier a few times in this course, that yes, laws of physics, laws of science are disproved, they have been disproved, and new theories replace these laws. The first case where a law was discovered to be false, at least the first case I can think of, was Albert Einstein. And that's today's topic. What Albert Einstein, when he discovered energy and mass being conserved as false, what did he replace that with? What's the correct idea? So what's the correct idea is the conservation of mass energy together. So the mass initial of a system does not often equal the mass final. It could, but it doesn't have to be. And the energy initial does not equal the energy final. Again, it might be, but it doesn't have to be. The key idea is this, E equals mc squared. And I just want to pause again. Remember, I said this before, that very often a lot of teachers say, no, laws can never be violated. And then they have E equals mc squared written somewhere in their classroom. This is saying these are false. It's the new law. And here's what the law is saying, that if a system has more mass in the beginning than it did in the final state, in other words, you could say it lost mass, it disappeared, there's less mass. Where did it go? Well, that's because a process was exothermic. And remember what exothermic means? It means that the process released energy out of the system. If the initial is smaller than the final, so in other words, the system somehow gained mass, it's more massive after something happens. That means it underwent an endothermic process. Somewhere, somehow, it absorbed energy from the outside. And so what happens is when energy moves in or out of a system, mass moves along with it. If something gains energy, it gains mass. If something loses energy, it loses mass. Give you an example. This bar, which we've used before in our physics course, has a mass of 500 grams. Now, if I heat this, well, I could heat it by holding it in my hand. It's colder than my hand, so my hand is giving energy, heat energy to this bar. The bar is no longer 500 grams. It's more than 500 grams. Now, are you going to put it on an electronic balance and see, oh, now it's 510 grams? No, you will not detect the change because we don't have any balances that are accurate enough to measure the gain of mass of this bar. It might be like a millionth of a gram or a billionth of a gram that I added by holding it in my warm hand, heating up the bar. You could figure out exactly how much mass by plugging in the energy. Maybe I put 10 joules of heat energy into the bar. What's the mass? This is the speed of light squared, 3 times 10 to the 8th. When you divide by 9 times 10 to the 16th, which is what this is, divide by a huge number, beyond a billion, beyond a trillion, you get a tiny bit of mass. So again, the mass change is so small, we often can't detect it. That's why humanity did not know things gain mass when they gained energy. Until Albert Einstein, clever guy he was able to figure out that minuscule change. He found it, and he wrote the new law of mass energy equivalence equals mc squared. Same thing when this cools down, it loses mass. Now, I want to point out, I'm not adding any particles. If you counted the number of iron atoms in here, I'll make up a number, 10 zillion, okay? Some huge number. I hold it in my hand, I warm it up, there's still 10 zillion atoms, but they're more massive. So I'm not adding any protons, I'm not adding any electrons, I'm not adding any neutrons or atoms. It's the same number of particles, it's just that when it's warmer, it's more massive, and therefore in gravity it's heavier. Fascinating, okay? Another point I want to make is that sometimes students, they don't quite understand this completely. Let's suppose I got a jar here and it's indestructible, and I put gasoline in here and oxygen. We know that's going to burn. And there's a little battery in there, and after a little timer, after a certain amount of time, the timer creates, so everything's inside. I close the lid down, and it's tight, it's closed, nothing can get in. A little spark detonates the gas, and the temperature in here goes from, 70 degrees Fahrenheit to 1,000 degrees Fahrenheit. Gets really hot, right? But this jar is indestructible, and I wrap it with a perfect insulator. Well, there's no such thing, but let's pretend a perfect insulator keeps all that heat in there, but it went up to 1,000 degrees. Most students would say, oh, it got hotter. If it gained energy, it gained mass. Not true. Because the energy, the thermal energy it gained, was because it lost chemical energy when the fuel burned. So the chemical energy lost was equal to the thermal energy gained. The system did not gain any energy from the outside world. Even though this got hotter, it's the same mass and the same weight. The only way for this to lose mass is once that fuel detonates, the heat goes out of the system. Once it leaves and goes into the air, that heat, and there's this cooling down, now it's losing mass, okay? So don't confuse hotter with more energy or temperature going up with more energy. Doesn't have to be the case. You could increase the temperature from all internal effects like the fuel in here, and it didn't gain any energy from the outside world, didn't gain any mass or lose any mass. All right, so let me create a pause to give you a chance to copy this beautiful theory down. Moving on. So there's a couple ways that on the Regents you might have to calculate using this formula. One method, let's suppose there's a system that lost 1 gram of mass for whatever reason. I'll say why in a second. So we got 1 gram, quote, lost. You could use E equals mc squared when you have the mass in grams or kilograms, but it must be plugged into kilograms. So 1 gram is 0.001 kilograms. Speed of light 3 times 10 to the 8th, front cover of the reference table. Square that, punch on the calculator, get 9 times 10 to the 13th joules, which is 90 billion joules. To give you an idea, that's like the original atomic bombs that the United States dropped on Japan. Each one had about that much energy. So when those bombs exploded, of course, all the pieces shot out in every direction and, of course, destroyed those cities. But if somehow by magic you could grab every single piece of those bombs that flew out every single atom that shot up into the atmosphere, and you could just pull them all back and weigh them or mass them after the explosion, and you know the mass of the bomb before the explosion, there would be a gram missing. And it's not because some atoms are still out there. You put them all back, but the energy went into the world, blew down buildings, burned down trees, right? All that energy went out. And so with the loss of energy is the loss of mass, even though you have all the original particles back. So that's an example where when the energy, like in an atomic bomb blast, is large, the mass change is now appreciable where you could more easily measure it. Another way, though, remember how when I mentioned when we first were studying photons, I said the unit of joule is like obnoxious when measuring a photon, no different than if you were to measure the length of a couch in miles. That's obnoxious. Miles is ridiculous. You better use inches or something like that. Well, very often when you're dealing with single atoms undergoing nuclear reactions, the mass change is like basically like less than a billionth or a trillionth of a kilogram. The kilogram unit is obnoxiously large when dealing with single atoms. So the unit that we use for single atoms reacting is on the reference table here. Where is it? A universal mass unit. I'll bring the reference table up front. It's a lowercase u. And just so you get an idea, 1 u is a tiny bit amount. It's 1.66 times 10 to the minus 27 kilograms, which is about the mass of a single proton or neutron. So now when we're dealing with one proton, it's 1 instead of 1.6 times 10 to the minus 27th, right? So 1 is more convenient. So let's suppose a reaction of a single atom, reacting in a nuclear fashion. Somehow the system gained 0.2 of these atomic mass units. So what that means is that it absorbed energy from the outside. If it's gaining mass, it's gaining energy from the outside. How much energy did it absorb? So instead of converting, you could convert this to kilograms and then plug in here and get an answer. But the more standard way that it's done on the Regents is you just do a dimensional analysis. You take your mass of 0.2 units and you multiply, you don't put an equal sign here, you multiply by a fraction to convert that to energy. Where's the conversion? Like I just mentioned, front cover of the reference table. So right here, front cover, right where my index finger is, you can see 1 universal mass unit, and you go over to this side right here and you see 9.31 times 10 to the 2 mega electron volts, which is the unit of energy. But that's essentially 931, right? 9.131 times 10 to the 2. The reference table likes scientific notation. So that's the conversion between units and mega electron volts. So what I'm going to do is I'm going to put the the mass unit down here because I want it to cancel and leave me the energy mega electron volts. Then so I have these units here. Then I look up what the numbers correspond to these units. I saw 1 mass unit to 931 mega electron volts. So the mass units go away and I'm multiplying 0.2 times 931. I get 18.6 mega electron volts. Remember, mega means 10 to the 6th. So that's the amount of energy this atom absorbed in the process of reacting in the nuclear fashion. So let me create a pause to give you a chance to copy these notes down. All right, so these are a couple quick examples, but what I want to do is do a little bit more involved example, so a couple of them so that you can be ready in case the Regents throws something a little bit more difficult at you. So give me a moment and I'll write my example right here. All right, so here is the reaction. We've got 2 hydrogens, different isotopes, This one has one neutron and one proton together. This has two neutrons and one proton. They're still hydrogen because they still have only one proton. They fuse and they make a helium and then a neutron, extra neutron kicking out. So to find the energy and whether or not it's released or absorbed, what we have to do is find the initial mass and find the final mass and compare the two. So the initial mass of the system. All right, so as you can see, what I've done is I've taken the initial mass of the system by just adding up these two masses and getting, this is what the system had for a mass before the reaction. After the reaction, we have these two, so we add up these two masses and you see 5.04. So you see the system gained mass, and that means it had to gain energy too. So that's what we're going to do. We're going to find the mass increase and the energy increase of the system. So the first thing, the mass change so there it is. We subtract final minus initial for any change. We've been doing that all year. Delta velocity was final velocity minus initial. So doing it all year, so now final mass minus initial, and you get a positive quantity. That means the mass increased, that's the change. And so now the energy, the last step, finally, we can start with the mass, and then we're going to do like a chemistry dimensional analysis. What we want to do is we want to put the mass units over here and the energy units over here. That'll cancel the mass units. We go to the front cover of our reference table. I won't go to the camera again to make you dizzy, but basically we look up that one universal mass unit. So the 1 goes with the U, and with the mega electron volts is the 931. So that goes here. And you see the mass units go away, multiply this by that, and you get the energy released, which is 9.01. So there is the answer. So let me create a pause to give you a chance to copy these notes down. All right, let's do another example. All right, so there is the reaction. We basically do the same calculation here. We need to find the initial mass of the system here and here. So that's the initial mass, just adding these together. The final is, well, we don't have to do any calculating. And you can see that we lost mass. The mass decreased. And so that must mean energy was released. We could find delta M, and then we could find the energy using a conversion like we did over there. So I don't need to solve that out. You can if you want, but I just wanted to show you an example that how you can detect that the energy, the mass decreased, and therefore energy went out of the reaction into the world and resulting in that mass decrease. So that's nuclear physics 2. Mass energy equivalence is the new, you could say, law. It's actually a theory, but it's a law in a sense that tells us how energy and mass truly work. Again, if energy is released out of a system, so is mass, even though there are no particles leaving. If energy comes in, mass goes up, energy goes up, mass goes up, even though no particles were added. Again, the two calculations, one is a conversion like this. The other is E equals mc squared, but that's only if you have the kilograms instead of the atomic units as we had up there. One final point, if you knew the energy, like let's suppose they gave you this, and they ask you for how many mass units were, how much it increased by, what you would do is you would put now mega electron volts on the bottom and the mass units on the top. Look up that 1 goes with the mass units and 931 goes with the mega electron volts. So now you're dividing to get your, mass, to get the mass. Okay. So you might have to convert the other way. Anything else I think there was something else I wanted to mention. I can't remember, so I guess it'll just have to be. So, let me create a pause to allow you to copy these notes down. This, and also, you might want to jot these down here. So go ahead and do that now. All right, so that was mass energy equivalence, energy changes, mass changes in a nuclear reaction. I hope you enjoyed the physics. I hope you enjoyed the video. I'll see you in the next physics video.